As a parent or mentor, you have the awesome opportunity to help a young person build a future. So if the future they want is in the military, take the time to learn more at todaysmilitary.com, because their success tomorrow begins with your support today.
Hi there, thanks for joining us on another edition of Space Nuts. My name is Andrew Dunkley, your host, and today on the program we are going to be talking about the big news of the week, probably the big news of the year, and that is the first image, official image, from the James Webb Space Telescope. It's only been announced in the last hour or two since we started recording, so it's fresh off the press, or off the president's desk, whichever way you want to look at it. We'll also be talking quantum communications, so we can talk to aliens. Apparently there's a new theory that this could work, and also new telescopes being built at Siding Spring Observatory, just up the road from where I am and where Fred used to work. And they will be detecting gravitational waves. We'll also be hearing from Ben in Dover, who has a question about gravitational waves. And Alex from New South Wales is apparently going to ask a question about the size of galaxies. It's boring, that is. That's all to come on this edition of Space Nuts.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2.
1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
And joining us, as always, is Professor Fred Watson, astronomer at large. Hello, Fred. How are you?
Very well, thanks. Very excited with all that's going on.
Man, it's just crazy town at the moment.
Yeah, it is.
The astronomy world is agog.
Agog, that's right.
Agog. It's not a word I get to use very often.
No. Yeah, I like agog. I think it's got a ring to it.
Yeah, we'll get to that in a moment. Of course, we've got plenty to talk about and some audience questions, as I mentioned. And you've got a studio guest, Fred. Are you able to share this with our viewing audience? If you're watching us on YouTube, get ready for a surprise.
Just to let everybody know that he still exists, there's Muscat. Our family cat, who normally doesn't come into the study here because he leaves copious quantities of hair wherever he goes, but he's been asleep there in the chair all morning and most of the afternoon, so he's still here. He doesn't say much these days.
He's doing cats proud, because that's what cats do best.
Yep.
It's good to have Muscat in the studio. Right, let us get down to business. And first on the agenda is this amazing image that has been delivered by the James Webb Space Telescope. There's been a lot of anticipation about what the first image would be, a lot of anticipation about how far-reaching the James Webb Space Telescope will be in its capacity to provide deep field imagery from far, far back in the universe. And it has not disappointed, Fred.
Not at all, that's right. So what we're seeing, and I would guess most of our listeners will have seen this, because I think it's going to be the cover picture on the podcast for today. It really is a beautiful image of a cluster of galaxies, which, as always, has a gobbledygook name. It is SMACS 0723. SMAC stands for Streaming Motions in Abell Clusters.
Okay.
And Abell clusters are clusters that were catalogued by George Abell, who I knew when he worked in Edinburgh for a while. So cluster is a cluster of galaxies. But of course, like so many of these giant clusters, its mass acts as a gravitational lens, magnifying and distorting the images of galaxies in the far distance behind it. And so this particular cluster shows up beautifully in, the kind of colours that you would expect. So, as you know, the James Webb Telescope is an infrared telescope. So it can look at the image in various infrared wavebands. And what you can do is sort of equate those to visible light wavebands, so that things that are in the far infrared show up as red in the visible. Things that are, in the mid-infrared show up as white. Things that are in the near infrared, in other words, not much redder than red. They'll show up probably as blue. I'm not quite sure how they did the color balancing in this image, but they've got it absolutely right because the nearby stars are blue. The relatively nearby cluster of galaxies is white, and the distant ones, as you might expect it, because they're highly redshifted, they look orange in color. Yeah. Again, distorted. So we're looking back here, the nearby cluster is 4.6 billion light years away. The one beyond it could be double that. Wow. I haven't seen the results of that, but it's a long way off. And what I think is most telling about this image, so this is being called Webb's first deep field image. And you probably remember, because we've talked about it before, the Hubble telescope produced a number of deep field images, deep being how far into the universe you're looking, how far into the past you're looking. And there was the deep field, the Hubble, I can't remember what, the ultra deep field, I think, was the last one. There were a number in between as well. But they took weeks of time on the Hubble Space Telescope to build up the imagery. I remember the first one, they chose the part of sky because there was nothing visible in it. And so they observed it for several nights or several days, because it doesn't matter in a space telescope, and finally got these deep fields. But it took up to weeks to get them. The James Webb first deep field was obtained in 12 hours. So that's telling you that, we now have a tool that can beat the pants off the Hubble Space Telescope. And that is no small achievement. And of course, that comes about because it's a much bigger telescope. The Hubble is 2.3 meter telescope. This is a 6.5 meter telescope.
Yeah, it's and that's really part of the reason why people have become so excited in anticipation of what it is capable of, and it's already showing its true colours. Boom, boom. The part that really blew my mind when I looked at the image and read the description from NASA, I'm sure you'll know what I'm talking about here. NASA says this image covers a patch of sky approximately the size of a grain of sand held at arm's length by someone on the ground.
That's right.
And reveals thousands of galaxies in a tiny sliver of vast space. I know we always talk about the vastness of the universe, but here we are looking at a distance of maybe 4 to 8 billion light years, and we're looking at something that only takes up space the size of a grain of sand held at arm's length.
Absolutely.
I mean, my word, it is awe-inspiring. It really is.
Yeah, it blew the president away as well. I don't know whether you saw the NASA broadcast when this was released, but President Biden, you could tell he was absolutely captivated by all this. It's fantastic to see such enthusiasm. And of course, Andrew, this is only the first of many. By the time our listeners are watching and listening to this, if they watch on YouTube, we expect another tranche of images to have been released. The kinds of things that we're expecting to see, in fact, I think we've got a fairly good list here. We'll see WASP 96b. Now, that is a planet. That's an extrasolar planet, WASP 96b. So it's going to be really interesting to see how that shows up. We're going to see the Southern Ring Nebula. That's a planetary nebula. We'll see, no doubt, a lot of detail in that. We're going to see a cluster of galaxies, a very compact cluster of galaxies called Stephan's Quintet. Very well known, very beloved of galactic astronomers or extragalactic astronomers, people who study the wider universe. These galaxies are physically close together and all interacting with one another. And of course, an object in our deep southern sky, the Carina Nebula, the Eta Carina Nebula, one of the most active regions of space in our local neighbourhood. So it would be really interesting to see what's going on in that too.
Yes. Who knows? We might actually be focusing our cameras on alien civilizations out there somewhere, and we don't even know it. But that dovetails beautifully into our next story.
Yes.
So all I'll say, just to finish up with the James Webb Space Telescope, is watch this space, as we've said, because there's some exciting things to come. It's really, I think it's fantastic that they've done so well, that it got in place. Yes, it's had a couple of problems that they've managed to overcome without any adverse effect, and now it's ready to do its job and Yeah, who knows what we're going to learn, Fred? Who knows?
Absolutely. That's fabulous stuff.
But yes, I mean, maybe we will be focused on alien civilizations, and maybe they'll be able to talk to us using quantum communications. Now, this is a theory that's been put together by some scientists who believe this might be mathematically possible, at least.
So this, Andrew, is a really very intriguing story, I think, that mathematical calculations show that quantum communication would be possible across interstellar space. And I know you and I have talked about quantum communications before, because over the years there's been successive records broken for how far you can send quantum encrypted signals. So what do I mean by quantum encrypted signals? Well, I was about to ask,
signals? I mean, what does this actually mean? I don't...
What does it mean?
Yeah.
And it's about entanglement. And so this idea that, if you've got a quantum particle in some state, for example, the spin of an electron, it can be entangled with a spinning electron. It can be entangled with another one so that they come together in a kind of unified sense and just look like a single quantum object. And then if you separate them physically, you can infer by knowing something about one of them, you can infer something about the other. Like if one's spinning one way, then the other's got to be spinning the other way. But you don't find that out until you actually look at one of them, and that breaks the quantum entanglement. And the way this has been used in real life, if I can put it that way, is in encrypted communications. And I think certainly the first really good experiments in this were done at the University of Vienna. And, they were talking about, first of all, a few meters and then a kilometer or so. And then I think it extended to maybe 100 kilometers. And then Chinese scientists got involved with this and started doing quantum communications from space. So I think the record at the moment stands at about 1,200 kilometers, and it's an encrypted communication from a spacecraft down to the ground, which has maintained its quantum superposition, to give it the technical term. I'm swallowing these words. In other words, that allows this encryption to take place and to be revealed by what's called the quantum key, which is the entangled particle or photon or whatever it is. So that's the basis of quantum communication. Not very well explained, I'm afraid. The problem is...
I'm still a bit confused, but...
Well, if you're confused, just think about what everybody else is confused. This cat here is absolutely out of his mind with confusion.
I can see that. Yes.
He's so stressed out.
Rendered unconscious.
Yes, that's right. As I said, it's fundamentally about using quantum encryption to provide a key to decode a signal that you've received, and that's perhaps it glosses over some of the tricks there. So the problem is, and the reason why there's been this succession or successively increased distances over which quantum communication has succeeded, is that as soon as you put a photon, for example, into space, it interacts with its environment, and that tends to degrade the quantum encryption. And so that's why people have improved the technology and successively managed to push quantum encrypted signals further and further. And as I said, it's now over 1,000 kilometers. It might even be more than that, because this is a field that has moved very quickly, because of course it has practical applications for things like banking. You're encrypting communications in a way that it's mathematically unbreakable. That's the bottom line. Unlike most encryptions, which aren't, quantum encryption may still not be, but it's as near as you're going to get to being mathematical unbreakable. So what's happened now is that actually they're scientists at the University of Edinburgh School of Physics and Astronomy, which is where I was educated, there in Scotland.
I can hear that.
And it rubbed off a bit. They've basically used mathematics to show that you could use these quantum communications across interstellar space. Never mind, a few meters in the lab or a few kilometers in Vienna or a few, a few hundred kilometers up and down to a spacecraft, they suggest that you could push them to interstellar space. And that's a really interesting thought, because it's such a secure form of message transmission. That is really the remarkable aspect of this. And what they suggest is that you could keep these quantum, it's called quantum coherence, when you've got your two particles which are still entangled. The coherence could be maintained for many thousands or hundreds of thousands of light years, including the gravitational pull of objects on the way, if I can put it that way.
Great.
If you've got gravitational interference, that doesn't actually spoil the coherence. And so what bottom line from this paper is that if there are other intelligent beings anywhere in the Milky Way, they might be trying to communicate with us using quantum encryption. And so
I can hear them now, Fred. They're saying, geez, these dumb schmucks haven't figured it out yet.
Yeah, we sent them the quantum key. Yeah,
sent them our supermarket list, and they're just ignoring us. So that might change the way that we do SETI, for example, if we're looking for signals that might bear some kind of hallmark of being quantum encrypted. I'm not sure what that would be, but I'm sure there is one. But there's a lovely throwaway last line. We're fans of the phys.org website, and their report on this ends with the sentence, they, and by they mean these researchers in the University of Edinburgh, they also suggest that quantum teleportation across interstellar space should be possible. Oh boy.
Put that one in your pipe and smoke it. That's such a neat idea.
Just to drag it back to my pea-sized brain trying to get my head around this, are they talking about the potential for instantaneous communication over vast distances using quantum entanglement via this mathematical method, which appears to use X-rays, I think?
Yeah, I think it does use X-rays, the work that's been done so far. Look, that's the $36 million question. I don't even know that it's the theory, because I think the signals still have to travel at the speed of light, but it's the encryption bit that's the instantaneous bit, because that's where the idea of entangled particles comes in. Now, this is territory that is full of pitfalls, and the perhaps naive way of looking at it, which I confess I do, is that if you look at the spin of an electron in one place and its entangled companion is 50 light years away, then you immediately know what's happening to the entangled companion. But that doesn't necessarily mean that you've got a signal that's breaking the speed of light, because the information is rather special. And I know a lot of physicists caution against this naive view that Einstein's speed limit of the speed of light is being broken if you've got entanglement. So we should tread rather carefully there. And I suspect we're not going to be either sending signals faster than the speed of light or indeed being teleported at faster than the speed of light. But it is a paper that's worth looking at. I confess I haven't looked at the original paper yet, but I should do.
Imagine if they crack it, though. Imagine if they're right on the money with this. Yeah. And we've found a new way to deliver messages into interstellar space or receive them. That's pretty exciting.
Well, it is, absolutely. Anything along these lines is, and you never know. There might be a Nobel Prize at the end of this, just like there is at the end of the James Webb Space Telescope.
Could well be, yes. But as Fred said, if you want to read up on this discovery, will we call it a discovery, or this theory?
Yes, I think it is. I think it's a discovery.
The phys.org website. It's just an excellent resource, that website. Really love it.
And it will send you to a Physics Review Letters article, which is where it's Physical Review D is the source of the paper.
Yeah. If you just do a search for quantum communications, you'll probably find it rather easily.
Probably will. Yes.
All right. Hopefully there's more to tell then.
Yep.
In the near future. All right. We're going to take a little bit of a break and a breather, although we've already done that at length today due to our communications problems. That's because we didn't take a quantum leap to solve it. But anyway, we will carry on. You're listening to, and in some places watching, Space Nuts with Andrew Dunkley and Professor Fred Watson.
3, 2, 1.
Space Nuts.
Okay, Fred, back to your old stomping ground now, up around Siding Spring Observatory at Coonabarabran, which is only around about 2 hours drive from where I am. Well, 2 hours the way I drive, an hour and a quarter for everyone else. But new telescopes are being developed that will be focusing on the detection of gravitational waves. Tell us all about it.
Yeah, so it's not a LIGO or anything like that, an interferometer that detects the actual physical shaking of space-time as a gravitational wave passes. What this is about, Andrew, is telescopes that can actually look for the visible light counterpart of some of the events that create gravitational waves. And that's important because even though we now have the 2 LIGO detectors, we've got the Virgo detector in Italy have joined them. The LIGO detectors, of course, being in the USA, and the Kagra detector in Japan, I think, is also online. So even though you've got these widely separated detectors to pick up gravitational waves in different parts of the Earth, and that lets you do a bit of triangulation to work out what direction the gravitational waves are coming from. It's still not very precise. And if you want to follow up on the details of the aftermath of an event like a neutron star pair colliding or something of that sort, then you need to see the visible counterpart, the visible flash. Right. And so that's what basically driven this development of, well, actually, the telescopes, and there are more than one of them, are called GOTO, GOTO, which is an acronym for Gravitational Wave Optical Transient Observer. And one of those is coming to Australia. It's actually it's a great acronym, I have to say. I like it very much. So the University of Warwick in the United Kingdom is one of the prime movers in this, but there are many collaborators, including Australian universities, in particular Monash University down in Melbourne, to have widely spaced telescopes that can look in both the northern and southern hemispheres that are all ready to go and immediately scan the sky, the part of the sky gravitational wave appears to come from. Even though you don't know it very precisely, you've got a rough idea where it is. So if you've got a group of telescopes that can scan that, can immediately home in on that bit of the sky once an alert has been received, and then start taking images, then what you might find is the aftermath, the flash of one of these events. Black hole gobbling up a neutron star or whatever it is that's sending ripples through space-time, the speed of light. So the story here is that the northern hemisphere part of GOTO has been in operation for some time, I think, and it's located in another place that I've worked at, actually, quite a lot in my history. This is the IAC, which is the Canary Islands Institute of Astrophysics. They are based in the Canary Islands, as you might know. They have telescopes both in Tenerife and on the island of La Palma, which is where I used to work in the Canary Islands. There's a big suite of telescopes there that were originally developed by the British in collaboration with the Dutch. And I did a lot of work there in my time. So one of the GOTO facilities is there. It's the Northern Hemisphere one. But here in the South, we are getting the Southern Hemisphere version. And in fact, I know that groundbreaking has taken place, I think this week. Been parts of GOTO stashed away in the UK Schmidt telescope's ground floor for quite some time. But I think the work on installing this telescope, and it's actually several telescopes, the work is going ahead already. So this is great news. It's really good that we are playing a part. One of the things that I think is worth stressing is that it is a fantastic testament to the staff and support and the management of Siding Spring Observatory, now managed, as it always has been. In fact, the observatory has always been managed by the Australian National University. through both their Facilities and Services Division and the Research School of Astronomy and Astrophysics, it speaks volumes for all the work that's been done there and the quality of the site itself, that they are still attracting new facilities to be built on that mountaintop very far away from you, Andrew, as you said.
Yeah. Can't see it from where I am, but don't have to drive very far before you start seeing those beautiful mountains in the Warrumbungle Ranges. And anybody who's never been out west, you're missing something spectacular. It's just when you're driving out of the town of Gilgandra and you're heading north towards Turawina, and you're just going through that area, you just see these amazing mountaintops in the distance, and they blow your mind the first time you see them. You just go, what on earth is that? It's just a beautiful, beautiful place, lovely national parks, and just a great place. And you can see the observatory on the top of Siding Spring there if you know where to look. But it sticks out like a sore thumb, doesn't it?
Yeah, well, it does. That's right. Yeah, I'm always reminded, Andrew. It's a moving experience to see those mountains.
It is.
And I remember, I think John Oxley's words in his journal when he first approached those mountains, which he did actually from the west, and he called it a stupendous range of mountains raising their blue heads above the horizon.
Indeed.
And then he went on to name it Arbuthnot's Range, which is a bit dumb because they've had a very ancient Gamilaré name, which is Warrumbungle. It means crooked mountains.
And that's exactly what they look like.
They do, that's right.
Yeah.
That's what they look like. So, yeah, marvellous that the observatory there, as I said, is still attracting new facilities. And GoTo is something that I'm sure you and I will be talking about again, Andrew.
I hope so, yes. And it also, I suppose, indicates how significant the study of gravitational waves is.
Yes, yeah.
You wouldn't be spending all this time and all this money and putting all these resources into something if it wasn't worth pursuing.
That's absolutely right. And, this has been heavily supported by the UK's science funding agency, the Science and Technical Facilities Commission. Is that the right thing? I can't remember. Agency, STFC. It's the Science and Technology Facilities Council, STFC. They've put $5.5 million into the project. Ooh. So they're putting their money where their mouth is.
Yes, indeed. All right. Well, we'll just tell people when these telescopes are set up, ready to roll, and certainly keep an eye on how they develop and what they can teach us with their detections. And we'll certainly make sure that we revisit this story in the not too distant future. This is Space Nuts. My name's Andrew Dunkley, and that is Fred Watson. Which way are you, Fred? I don't know. Stick around. More to come.
Yeah.
Space Nuts.
Okay, Fred, let's tackle some... I keep looking up to the camera where it's not anymore. It's down here now. Let's go to our questions, and we're going over to Dover, where Ben, he's basically continuing what we were just talking about with gravitational waves.
Hi, I'm Ben Harding from Dover in England. I've got a question about gravitational waves. Will gravitational waves be subject to gravitational lensing? So if a wave comes from behind a cluster of galaxies, will it be magnified like light is? Thanks very much for an amazing podcast, guys. Cheers.
Cheers, Ben. Thanks for the question. Yeah, that's a good question. We talk about light and the things behind gravitational lenses being magnified and being able to, the effects of a gravitational lens. But does a gravitational wave, is it affected by gravitational lensing?
It's a great question, and the answer is, yes, they are.
Oh.
So, and I have the authority of the LIGO collaboration behind me to say this, because I'm looking at their webpage at the moment. I have checked this before, and, it's surprising what the phenomena are that gravitational waves are subjected to. They are significantly different from light waves, which are transverse waves. They're what are called quadrupole waves, which means that space-time vibrates in a much more complex way. But let me just read from the LIGO Scientific Collaboration's website. What can gravitational lensing do to gravitational waves? Like electromagnetic waves, gravitational waves can be gravitational lensed by intervening objects such as stars, black holes, galaxies, and galaxy clusters. However, There's always a however, Andrew. While the theory behind the lensing of gravitational waves is similar to that of light lensing, the methods to detect it are entirely different due to fundamentally different sources and detectors. And, that's a reference to is exactly what we've just been talking about, that we don't have yet a way of imaging gravitational waves to show the details of exactly where they come from. We only get a rough idea of where they come from. So if, for example, you've got gravitational waves that pass by a black hole and those going one side of the black hole take a little bit longer to get to us than those going on the other side, and you form a double image, then that's not going to be visible to us. However, the timing might be visible to us. But yes, the answer to the question is yes, it's a subtly different phenomenon, but they are subject to gravitational lensing. And
how interesting.
Yeah. So thanks, Ben. That's a great question.
Yeah, because we were only really, well, I was only considering that that objects would be affected by gravitational lensing, and I wouldn't have thought something as fast and as invisible as a gravitational wave would be affected. That is fascinating.
It is. I mean, in fact, the difference is not too startling, because even when an object is distorted by a gravitational lens, it's actually the light passing around through that gravitational lens that's being distorted. And light is kind of akin to gravitational waves in the sense that what we're seeing is a wave motion that's being transmitted through space.
Yeah. Yeah. All right. Thank you, Ben. Now we'll go to Alex, who's from a lovely, it's actually a sordid, nasty, horrible little place called Bellingen in New South Wales. It's actually a glorious part of the world.
It's delightful, yeah.
Yeah. Alex is asking about galaxies. This is really good too.
Hi, Fred and Andrew. It's Alex from Bellingen. Congratulations on your 300 shows. May there be many more. Okay, straight into my question. It's about the apparent size of galaxies. It's common understanding that the further away an object is, the smaller it appears to our eyes. I guess you could say the object's angular size reduces with distance. Just look down a long straight road lined with power poles, and the poles appear smaller the further away they are. But I've heard this seemingly obvious relationship between distance and apparent size does not apply to galaxies. Well, it does to a point, but at some distance away from us, the apparent size of galaxies stops getting smaller and then begins to increase the further from us they are. Have I heard that right? And if so, how the heck does that work? Thanks, and keep up the good work. All the best.
Oh boy, you tell us, Alex. That sounds bizarre, Fred.
It does, doesn't it? It's an extraordinary thing, but it is actually true. And it's a real illustration of the fact that we live in a universe that has peculiar properties. And it's basically the fact that we live in an expanding universe that causes this phenomenon to happen. Because if you go through the mathematics, and actually there are places on the web where you can find some nice diagrams that show how this works. The further away you look, you get to a certain point beyond which things don't look any smaller, because the universe is expanding. That's the best way to put it. So if you think about, our Andromeda galaxy, nearest neighbor, which is altogether something like 2 degrees on the sky, at its distance of about 2.5 million light years away. So if you envisage Andromeda, we know what it's like. We've all seen pictures of the Andromeda galaxy. Beautiful elongated spiral because it's tilted over towards us. 2.5 million light years away. If you took that galaxy further and further away, of course, it would start looking smaller and smaller because it's getting further away. The laws of physics work pretty normally over small distances. But once you get to distance, which is actually, the distance varies because Depends on your model of the universe. But I can give you the technical answer. It's at a redshift of about 1.5. And that's sort of a distance that's measured in billions of light years. We're probably talking about something like 8 or 9 billion light years. Once it gets to that distance, it hits a minimum size, which is about 1,000th of a degree. Remember, it's 2 degrees at its present distance, but it gets down to this 1,000th of a degree mark. And even though then, keep on moving it away, it doesn't actually get any smaller. In fact, it starts getting a bit bigger. And that is totally bizarre. But it's just about the way light behaves in an expanding universe.
Wow. And is this something that would be able to be demonstrated by the James Webb Space Telescope?
Exactly so. I think we'll see physical proof of this happening with the James Webb Space Telescope when they find that there are galaxies that don't seem to get any smaller, even though you're looking at them further and further away.
Quite incredible. That's the same effect I have when I hit a golf ball. It doesn't get smaller and smaller. It stays about the same size.
Yes.
Which suggests I'm not really hitting it very far at all. Never mind.
If you hit it far enough,
Alex.
It'll start getting bigger. It's coming back to you.
Yes, absolutely. Thanks, Alex, and I hope all is well in Bellingen. I know you've been getting rained upon by cats and dogs and camels and who knows what else in recent times, so hopefully it'll start to dry out soon. Now, that brings us to the end. Fred, we got there eventually. We've had all manner of technical problem today. I know we got some live questions from people watching on YouTube. Apologies. I did mean to ask them, but Fred's got a hard deadline and please save them up for the next time we're on, which will be this time next week, and I'll try and get to them then. Do appreciate the feedback from the live audience on YouTube, Facebook and Patreon. But if you do have questions for us and you can't ask them live, you can do it via our website, spacenutspodcast.com and spacenuts.io. You can use either URL and ask your questions via our various links, the AMA tab, or send us your question tab on the right-hand side. And of course, while you're there, check everything out and visit the Space Nuts shop, check out the news tab. Look at becoming a patron if you like, and don't forget to send your reviews through to your podcast platforms, because more reviews, more listeners, and more people to share all this knowledge with. Fred, thank you so much for your patience and your input today. Always a pleasure. You are a true gentleman.
So are you, Andrew. You worked very hard on that. I'm now wearing 2 pairs of headphones because I am about to join another meeting, but always delightful to hear from you. We'll speak again next week.
We will indeed, Fred. Thank you so much. And thank you for listening to Space Nuts, episode 313. From me, Andrew Dunkley, good to have your company. We'll catch you on the very next episode. Bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Available at Apple Podcasts, Google Podcasts, Spotify, iHeartRadio, or your favorite podcast player. You can also stream on demand at Bytes.com.
This has been another quality podcast production from Bytes.com.